Let's briefly review common multivariate techniques. Factor analysis, including both principal component analysis and common factor analysis, is a statistical approach that can be used to analyze interrelationships among a large number of variables and to explain these variables in terms of their common underlying dimensions or factors. The objective is to find a way of condensing information contained in a large number of original variables into a smaller set of variates with a minimal loss of information. An example could be customers' rating of a fast food restaurant. The objective of multiple regression analysis is to predict the changes in the dependent variable in response to changes in the independent variables. For instance, a company's sales from information on its expenditures for advertising and the number of salespeople. Cluster analysis is an analytical technique for developing meaningful subgroups of individuals or objects. The objective is to classify a sample of entities into a small number of mutually exclusive groups based on similarities among the entities. In the cluster analysis, unlike discriminant analysis, the groups are not predefined. An example for the application could be determining customers' types based on their habits. Discriminant analysis is used in situations in which the total sample can be divided into groups based on a non-metric dependent variable, and it is used to understand groups' differences and to predict the likelihood that an entity, it could be individual or object, will belong to a particular class based on several metric independent variables. Did you know that Internal Revenue Service, IRS, uses discriminant analysis to compare selected federal tax returns with a hypothetical normal taxpayer return, of course at different income levels, to identify the most promising returns and also areas for audit. Correspondent analysis is a recently developed interdependence technique, and it facilitates the perceptual mapping of objects, products, or persons on a set of non-metric attributes. Example is a brand preferences with demographic variables such as gender, income categories, occupation. In the 1930s, three different people, Ronald Fisher in UK, Harold Hotelling in US, and Prasanta Mahalanobis in India, were trying to solve the same problem through three different approaches, and later their methods were combined together to form what we call today discriminant analysis. Discriminant analysis is a technique when dependent variable is categorical, nominal, non-metric, and the independent variable is metric, continuous. And single dependent variable can have 2, 3 or more categories. For example, male versus female, purchases versus non-purchases. Of course, groups must be defined a priori. Frequently, discriminant analysis is used as a dimensionality reduction technique for pattern recognition or classification and machine learning. Discriminant analysis involves deriving a variate. So it is a linear combination of 2 or more independent variables that will discriminate best between the objects in the groups that define a priori. Discrimination is achieved by calculating the variate's weights for each independent variable to maximize the differences between the groups. The variate for discriminant analysis, also known as discriminant function, and is derived from a linear equation where Z is discriminant score, alpha is intercept, W discriminant weight for independent variable, and X is independent variable. The score is a summation of the values obtained by multiplying each independent variable by its discriminant weight. By averaging the discriminant scores for all the individuals within a particular class, we can arrive at the group means, centroid. And when analysis involves 2 groups, there will be 2 centroids, and 3 groups will be 3 centroids, etc. Model looks at the score from each function and uses the highest score to allocate a case to a class, prediction. And we call this scoring function the discriminant functions. Linear discriminant analysis takes a dataset of cases, also known as observations, as input. And for each case, you'll need to have a categorical variable to define the class and several predictors, predictor variables, which must be numeric. And we often visualize the input data as a matrix where each case is a row and each variable is a column. Think of each case as a point in n-dimensional space, and n is a number of predictor variables. So every point is labeled by its own category or class. So this analysis is applicable to any research question with the objective of understanding group membership. It can comprise individuals, customers versus non-customers, firms, products, and any other object that can be evaluated on a series of independent variables. We can also consider discriminant analysis as a type of profile analytics or analytical predictive technique. To illustrate the basic premises of discriminant analysis, let's examine a sample research involving two groups, purchases versus non-purchases. Suppose we have a company that needs our analysis to determine whether one of its new products will be commercially successful. To assist in identifying potential purchasers, we obtain rating scale on three characteristics: durability, performance, and style. But instead of relying on each scale as a separate measure, we hope that a weighted combination of all three would better predict purchase likelihood of customers. Here we have a panel of 10 potential purchasers. Let's examine this table to identify potential discriminating variables. First, there's substantial difference that separate the mean rating groups of X1, which is durability, between would purchase and would not purchase customers. Notice 7.4 group mean for would purchase customers, and 3.2 is a group mean for would not purchase customers, group 2. Durability appears to discriminate well between the two groups and is likely to be an important characteristic for potential purchasers. In contrast, if we look at X3 style, the difference between two group means is quite small, and it seems that X3 will not discriminate well between two groups of purchasers. A graphical illustration will help us to further understand the nature of discriminant analysis. So here we have two groups, A and B, and two variables, X1 and X2. If we draw a straight line through 2 points in which the ellipses of A and B intersect, if we project this line to a new z-axis, we can see the overlap between the univariate distribution A and B. And z-axis expresses two variable profiles of group A and B as a single numbers, the discriminant scores. There are several types of discriminant analysis. Linear discriminant analysis or canonical discriminant analysis assumes that the observation within each group or each class are drawn from a multivariate Gaussian or normal distribution, and the covariance of the predictor variables are common across all levels of response variable. Quadratic discriminant analysis also assumes that observations are drawn from Gaussian distribution. However, it assumes that each class has its own covariance matrix. So the predictor variables are not assumed to have common variance across each level of Y. Dichotomous discriminant analysis, it's analysis where Y variable has two groups. Multiple discriminant analysis when we have 3 or more groups. And finally, stepwise discriminant analysis where we use forward, backward variable selection methods for classification. Discriminant analysis has multiple applications in a variety of domains. For instance, in banking, we can use it for bankruptcy prediction. Bankruptcy prediction is based on accounting ratios and other financial variables, and we can use discriminant analysis to explain which firms entered bankruptcy versus survived. Did you know that linear discriminant analysis was the first statistical method applied to systematically explain bankruptcy prediction? In marketing, we can use it to determine the factors which distinguish different types of customers or products on the basis of surveys or other forms of collected data. In biomedical studies, we can assess the severity state of patient and prognosis of disease outcome. For instance, during retrospective analysis, patients can be divided into groups according to severity of disease, mild, moderate, or severe form, Using these variables, discriminant functions are built which help to objectively classify disease in a future patient to mild, moderate, or severe forms. We can use several stages to build our workflow for discriminant analysis. We need to determine if statistically significant differences exist between two or more groups. We also need to identify relative importance of each of independent variables in predicting group membership. We need to establish the number and the composition of dimensions. We need to develop procedures for classifying objects into groups and then examining the predictive accuracy or hit ratio of discriminant function. In stage 1, we evaluate group differences and classify observation into groups. In stage 2, we select independent variables and create our analysis, training, and holdout samples. In stage 3, we test and check for assumptions, normality of independent variables, linearity of relationships. We look if multicollinearity exists among independent variables, and we look for equal dispersion matrices. In stage 4, we need to determine optimal cutting score and specify criterion for hit ratio, and look for statistical significance of predictive accuracy. In stage 5, we interpret our functions and we validate our results using split sample or cross-validation. To partition our data into training and holdout samples, we will use create data partition function from library caret. Library mass will provide us with discriminant analysis function, and we use dataset banking authentication. This is data about distinguishing genuine and forged banknote, and it was extracted from images that were taken from banknote specimens. Our predictor variables must be numeric. Recall we need independent variable as metric and target dependent variable is non-metric, categorical. So we're going to convert class, our target variable, into a factor. Then we'll partition our data into 70% of training data set, and we retain the remaining data as a holdout. After we built our model, we can evaluate model performance on this holdout data set. So in our data, we have a class variable, and we have 4 predictors: variance, skew, kurtosis, entropy. All those four predictors are extracted features from the banknote images. From our partition data sample length, we can conclude that indeed our training data set is 70%. We can look closely at the correlation coefficient between each of 4 predictors. We can use package psych and use the function pairs panels, which displays variables along the diagonal, scatter plot in the lower triangle, and correlation coefficient in the upper triangle. Let's move to step 3, building our model. We're going to pass as a first argument predictors and outcome values. Target will be the second argument in the function. Notice that the syntax for LDA is identical to the function of LM, linear modeling, and also to GLM, except we don't mark the family option. The model summary provides us with variable metrics. We can look at group means. These are the averages of each predictor within each class as estimates. We can look at the counts. Scaling exhibit a matrix which transform observation to discriminant functions. We can look at the ratio of between and within group standard deviation. We can also look at the prior probability. In other words, 56% of our training data observations represent class 0 and 44% of our observation represent class 1. And recall, class 1 and 0 represent classes of genuine or forged banknote. Group separation can be plotted using plot function from the mass package on the right. It shows us a stacked histograms of values of discriminant function from 2 different groups, group 0 on the top and group 1 on the bottom. The more overlap between these 2 classes, the greater the error rate will be. Using partimat function from the CLAR package will give us a slightly alternate way to plot linear discriminant function. Partimat outputs array of plots for every combination of 2 variables. You can think of each plot as a different view of the same data. And we have colored regions that delineate each classification area. You can see that any observation that falls within a region is predicted to be from a specific class. And each plot also includes the apparent error rate. You notice the highest error rate is given for kurtosis and entropy, 0.4. And the smallest error rate we can observe between variance and skew, which is 0.1. In the next step, we can use the predict function to generate predictions for the training partition. We're going to pass the model in predictor variables, and the class component contains the predicted class values. Then we can use the table function to generate a two-way cross table. We can check now how our model actually performs on a training partition. Please note that your results may slightly differ because of random partitioning. So the total number of correctly predicted observations is the sum of diagonal. So we have 510 plus 427, it's 937. So we can calculate the accuracy of predicted observation divided by the total number of observations. In the step 7, we can evaluate our model using validation partition, hold out sample. We follow the same step and generate prediction, but using now a hold out data set. And when we build our testing set table, we can look again at the accuracy. So 220 plus 183, it's 403, divided by 411, which is the total observation, and we obtain 98% of accuracy. You can also try a stepwise discriminant analysis from the library CLAR. We start by building step class. The first parameter is our predictors, and the second one labels. We can include both directions, and if we have many variables, we can include starting variable, or you can skip that to include all of variables. When we plot this object and also print the summary, we notice that only variance, one predictor, is retained as the best model. And if you look at the plot with estimated correctness rate, from start, the correctness rate increased when we add and retain variance. It is something for you to explore in the future if you have a large amount of variables and you try to build linear discriminant analysis on stepwise selected features.